Si sente? Sì. Good evening. I'm Franco Desiato from the National Environmental and Research Protection Agency here in Rome. I'm going to chair this second part of the afternoon section of section 4. And before starting with the first presentation, I just would like to say that we have two young career researchers which are helping the work, are doing the work of rapporteurs in our sections, and they are Ilona Valishuo from the Finnish Meteorological Institute and Ellen Bertnell from the Stockholm University. So I leave to the first presentation, which is from Simon Chabriat from the Bayer IASB, and the title is of his presentation is Mean Age of Stratospheric Air since 1985, Large Disagreements between 5 modern reanalyses.
Yes, and good afternoon. BIRA IASB is the Belgian Institute for Space Aeronomy. This work was done with many colleagues from Belgium and elsewhere in Europe. The title has changed a little since I submitted the abstract. Now it starts in 89. I will explain why. And also I toned down a little the title, saying that those results are obtained with a kinematic transport model. This work belongs to the SPARC Reanalysis intercomparison project, and it delves on the Breuer-Dobson circulation in the stratosphere. So a small reminder for those of you not working in the stratosphere, the Breuer-Dobson circulation is induced by planetary and gravity wave activity and puts in slow motion the air masses in the stratosphere. It results from a residual circulation shown on this scheme with the white arrows, and also two-way mixing, that's the wavy orange double arrows. And this mixing also happens across transport barriers, which are typically the tropics, extratropics, tropical barrier, and the polar vortex barrier. And there's also mixing across the tropopause. And to evaluate how the Breuer-Dobson circulation is represented in a reanalysis or also in a general circulation model, we have a handy diagnostic which is named the age of air, or more precisely the mean age of air. It's the transit time for an air mass going up from the surface. It very quickly reaches a tropical tropopause, and then much more slowly will follow the residual circulation to various places in the stratosphere, and then also with mixing. So the age of air is simply about how much time does it take. That time is on the order of years. And it's practical because we have observational estimates of this diagnostic with tracers like CO2 or SF6, which monotonously increase with time. It's roughly speaking, it's simply the time it takes for some region in the stratosphere to have the same mixing ratio of that tracer than it had a few years earlier at the tropopause. It's also easy to model with a synthetic tracer, which increases at the surface. And as such, it's a diagnostic of the Breuer-Dobson circulation strength, and it is used to evaluate general circulation, chemistry circulation models, and also reanalysis. For example, it was used to show improvements in ERA interim versus ERA 40. When we evaluate reanalysis, we use offline transport models, and there are two different kinds of transport models. Some of them are diabatic, and they are vertically gridded using potential temperature with vertical motion between those theta levels from the heating rates of the reanalysis, while other transport models are kinematic, and they use the hybrid pressure vertical grid, which is native to the reanalysis, and the vertical motion is simply deduced from mass conservation as in the weather prediction system itself. So here just a small slide about the methodology and the offline transport used to do this study, because the goal is really to try to put all reanalysis on the same foot. It's a kinematic model that we are using, so we take as input only zonal and meridional wind and surface pressure. They are converted to vorticity and divergence in spherical harmonics just because that's the way, that's the primitive variables in the IFS system of ECMWF, and our transport system was originally developed only for ECMWF. We run on a coarse horizontal grid at 2 degrees by 2.5 degrees. And in order to do that, to avoid aliasing errors, all the reanalyses are identically truncated to spherical harmonics. We keep only the 47 terms. So it's T47. Each reanalysis, on the other hand, is run on its own original hybrid pressure vertical grid. And we did the exercise with ERA interim, MERA2, MERA, JRA, and CFSR over the period 1980 to 2015. About setting up the intercomparison, the initial conditions have some importance because we want the intercomparison to start as early as possible, but we have no data before 1980. So before 1980, just to find some initial conditions which are independent one from each other, we do what's called a fixed year initialization, 20 years of fixed year 1980. And then to find out how long this initialization has an influence, I did another sensitivity test with 40 years of 1981 instead of 1980. And I could see that it took 9 years in all cases. This is just an illustration with one-time series, but I checked this all over the place, that there's negligible differences after 9 years, which then I take as spin-up. And so that's why I'm studying the variations after 1989. And what you can already see on those time series, which are taken at 50 hectopascals, more or less 20 kilometers altitude, so in the lower stratosphere, in the mid-latitude, in the northern middle latitudes, is that there are large differences between the reanalyses from all points of view. The absolute values of age of air are quite different. Also, the seasonal amplitude will depend a lot on the considered reanalysis. The QBO cycle, which you can see very clearly in some reanalysis, here it is ERA interim, and much less in some other reanalysis. And then the trends, which are a matter of debate among people interested in how the Brewer-Dobson circulation may be changing due to climate change. Observational effects, we've been shown previously by Masatomo the importance of the hiatus due to ETOV's satellite observations, which were introduced starting in 99 or 98. This can be seen clearly mainly with MERA2 in red, where you see that suddenly there's a change of behavior, especially with the amplitude of the seasonal cycle, which decreases and lets QBO be seen more clearly. I will go back on this. But you see, just with this comparison of time series, it's rich in information and large disagreements. So we first will look at average values between 2002 and 2007, so the more recent period. Usual manner to look at it is first to have the latitudinal cross-section at 50 hectopascal, 20 kilometers, compared with a set of historical observations, which have been used also in the CCM-VAL intercomparison of climate models. And you already see that this spread between the 5 reanalyses is quite large and reaches 1.5 years at the poles, with a behavior that we will see throughout the study, that MERA2 and MERA have the older age of air, and JRA55 the youngest, while CFSR, CFSV2 is kind of young in the southern hemisphere and intermediate in the northern hemisphere, where it finds just the same thing as ERA interim. What we find here at 50 hectopascals is also valid higher up in the stratosphere, both for the tropics and the mid-latitudes. Now it happens that due to mixing, actually, in order to look at the tropical ascent rate, one needs to look at the difference of age of air between the middle latitudes and the tropics. And that gives information about the tropical ascent rate. It's what you see here. And then it gets quite interesting that despite all those large differences, when you do the difference, you see that you have 4 reanalyses agreeing quite well with a gradient smaller than observed, which means too fast ascent above 50 hectopascal, except for MERA2, which has an outstanding behavior and seems better maybe in the middle stratosphere, but to ascend too slowly below 50 hectopascals. There's also a time series of observations of age of air in the middle latitudes, the northern middle latitudes, which have been collected by a team at the University of Frankfurt, and which have been used to try to see if there's like significant trends of age of air or not. Of course, those balloon observations, that the symbols and the error bars, they're very sparse. So you see, you have both inner error bars for those observations and outer error bars. The outer error bars represent the sampling uncertainty, the fact that it's a very sparse data set. So we will try, when we compare with the model results, to just focus on those reanalyses which get outside of those outer error bars. You see that this is the case for, especially for MERA2 during the 1980s, which is really too old. CFSR during the 90s, which is really too young. JRA afterwards during the early 2000s. Okay, and now if we go back to ERA interim, which is somewhere in the middle, we see that it has a weekly positive trend from 1990 to 2010. But actually, if you consider the whole period, it's really a very, very weak trend. And there's no overall trend after 2000. Also, I will come back later on that, the fact that there is large disagreements not only between the absolute values, but also between the trends in each reanalysis. Now, I would like to remind everyone that those results are not directly out of the reanalysis. They are obtained through an offline transport model. So now I've shown several times that MERA2 in red stands out. And that's actually the reason why this research is still not submitted, because I spent some time trying to figure out what I had did wrong with MERA2. I would say that's the slave point of view, you know, because we take the reanalysis as input. And so many things could have gone wrong with MERA2. First, because there are 2 types of products. The analysis from the 3DF GAT method, I think, and then another type of product which is recommended for studies like this one, which includes the incremental analysis update. It's called ASM. That's what's recommended for transport studies, but that's what I used. There has been a proposal to use 6-hour time averages for transport with MERA, but this is not done with any of the other reanalyses, so I didn't want to do it either with MERA or MERA2. And there are some age of air studies which use SD-WACAM, that's the WACAM climate model, nudged towards MERA, but all those studies use MERA and not MERA2. So they did not help me much either, until I finally went back to the literature and thought maybe the master is wrong. And indeed, as Masatomo showed earlier this afternoon, if you look simply at the zonal wind at Singapore, before 1995, you see that the zonal wind in the tropics has very serious issues, basically with a QBO missing, because there are spurious semi-annual variations in the 80s and in late 93, especially during this early phase of the QBO. That's the results which were published by Kawatani et al. But in the meantime, there's also the MERA2 paper itself, which showed the same thing, and a paper under review, part of SRIP, which shows the same issues. Okay, since we have this long time series, we can run a multilinear regression model in the usual manner, as was similar to what was shown by Masatomo already. And here I only want to show the amplitude of seasonal variations to say that there's broad agreement, except again for MERA and MERA2, and the sign that they disagree with depending on the considered period, very large difference in amplitude depending on the period. Now the trends are the dipole structure in the latitudinal structure of the trends. There has been lots of debate recently about the fact that age of air is getting older in the northern hemisphere while it's getting younger in the southern hemisphere over the 2002-2012 period from EPAS observations. And this is confirmed by this study. It was already confirmed by previous studies using ERA interim. So ERA interim allows to confirm the dipole structure. But this dipole structure is not so significant when you extend the period in time. It becomes much less significant simply by extending 3 years further in time. The white crosses, if you see them here, mean that the sign of the trend is not significant. So even the dipole structure itself is put in doubt if one dares to use the whole period of the reanalysis. Beatrice Mangesans has a poster using ERA interim and doing this kind of comparison. Now, if we add the 4 other, and this will be my last result, if we add the 4 other reanalyses, we see that no one agrees, really. First of all, only ERA interim has a dipole structures, the other ones do not. And then the trend of age of air, as I showed with the time series at the beginning, they're often not significative, but there's only CFSR, which agrees broadly on the fact that it's getting younger on the more recent period, but older over the whole period. And then the 3 other reanalyses show exactly the opposite. So it's really very difficult to find the common behavior in all these reanalyses with respect to the trend of age of air. And this spread is at least as large as the spread of age of air among circulation models. So the take-home message here is that at least using a kinematic transport model, one should not rely on analysis to be sure about what's the correct age of air for a climate model. So the conclusions are there. I don't have the time to read them all. I just talked about the spreads. The fact that MERA2 is an outlier and that there are also large disagreements in the trends. And this paper should be submitted to the special issue of ACP before the end of the year. Thank you.
Thank you. Are there any questions?
Yes, Stephen Paulson, GMAO. I understand that you choose to want to get snapshot time steps from all of the reanalysis to do the comparison, but we do actually recommend that the 6-hour average fields that we produce and release are the ones that should be used for transport from MERA2. So that's more of a comment than a question.
Okay, that's correct. I can say that I did some tests where I changed the way the winds are used during the 6 hours, and I did not see any large impact. And considering the large difference in zonal wind, I think that the explanation more probably lies there.
Yeah, Sean Davis, NOAA. You've looked at tropical ascent rates being too fast. Have you looked at changes in mixing to see if those explain some of the differences that you see?
No, I didn't do it. Actually, it looks like with simple mean age of air, the way I do it, the mixing cannot be evaluated. This requires some other diagnostic, maybe considering the spectrum of age of air rather than its mean value. And so this is not done at the present time.
thank you. And now I would like to invite for his presentation Michael Mayer from the University of Vienna. And the presentation has the title Towards Consistent Diagnostics of the Coupled Atmosphere and Ocean Energy Budgets. The floor is yours.
Good afternoon. So this is work I did back at University of Vienna. And it's all about energy budgets. And yes, the energy budget framework is used for climate applications in various ways. And I would like to talk about one specific application, which is to derive net surface energy flux as a residual from satellite-based net radiation and atmospheric energy divergence. This method has several advantages over parameterized fluxes. First of all, it's based more on analyzed fields rather than forecast fields. Second, as long as the satellite radiation is globally unbiased, also the inferred surface fluxes will be unbiased in a global mean sense. Plus, they are thought to be relatively stable in time compared to parameterized fluxes. However, if we look at these inferred surface flux fields, we find quite large discrepancies with other observation-based estimates. And here I would like to reconcile the currently used diagnostic methods. And I hope I will be able to show that a large part of these discrepancies are actually related to shortcomings in current practices in how the energy budgets are evaluated. So what I'm showing here is just the standard energy budget equation for the atmosphere as it has been used in dozens of publications over the years. And I will exclusively talk about the steady state, so you will not see any tendency terms. So this equation just says that the net surface energy fluxes can be computed as a residual from the net radiation at the top of the atmosphere and the lateral energy divergence in the atmosphere. And the net surface energy flux is defined as usual as the sum of latent and sensible heat flux and the net radiation at the surface. And just for illustration, I put here long-term averages of satellite-based radiation on the left and the atmospheric energy divergence on the right based on era interim fields. If we put these two together, we get inferred net surface energy flux, which looks quite realistic, so the patterns look all right. However, if we compare these fields to independent estimates of the net surface energy flux, in this example, it's this, as has been shown already earlier these days, it's the sum of series EBUF surface radiation and OA flux, turbulent fluxes. And you see on the two plots essentially just show the difference of budget-based surface energy flux and the series and OA flux-based surface energy flux. And these two estimates are, the upper estimate is based on era interim and the lower one is based on JIA55. So what you see is rather large differences, and the patterns are quite similar, and they essentially show a P minus E pattern, which is quite interesting. And we asked the question where this pattern is coming from. And for this, we took a closer look at the total energy budget equation. And in the first step, we can just write out the divergence term. And this is just the divergence of horizontal wind times moist static energy plus kinetic energy. and we can further decompose the divergence term into an advection term, where we have the gradient of moist static energy and kinetic energy, and on the right we have a mass divergence term, where we have absolute m plus k. And there are 2 points I should make here. So in a steady state, and if dry mass is conserved, the mass divergence reduces to moisture flux divergence, plus in the mass divergence term we have absolute moist static energy, and this means this term scales with temperature itself. So this means if we use a different temperature scale, we will get a different result. And just to illustrate this, I put here the equation for the difference in the inferred net surface energy flux, either using Kelvin scale or Celsius scale. And we end up with this term over there, which just scales with 273, which is the difference between the temperature scales, and Cp, which is specific heat of air, and of course the moisture flux divergence. So I will call this term simply the H naught term, so it's a kind of constant reference enthalpy term. And in the plot you see the resulting field. And so first of all, the values are quite large, so they go up to 30 watts per square meter in the ITCC. And they, of course, have a pronounced P minus E structure because it's driven by moisture flux divergence. So you might ask now, which inferred surface flux is correct? Shouldn't energy fluxes be independent of the used temperature scale? And I agree. So this difference essentially hints to a shortcoming in the diagnostic practices. And for this, I'm showing this hopefully not too complicated schematic of an atmospheric ocean column. And so the upper part is atmosphere, the lower part is ocean, and the arrows indicate material and non-material energy fluxes across the boundaries of these boxes. So this rather long equation is again just the divergence in the atmosphere, and so over here you have kinetic energy and potential energy, latent heat, and for the enthalpy I decomposed it simply into enthalpy carried by dry air, this scales with 1 minus Q, and enthalpy carried by vapor. And also the H naught term shows up again. This is just the reference enthalpy that I just explained on the slide before. And you also have here the vertical surface fluxes, and so this arrow is just the well-known net surface energy flux, and the enthalpy flux associated with evaporation, Fe, and the one associated with precipitation, Fp, they are implicitly set zero. Nobody, so it's usually assumed to be negligible. So if you look at the schematic, you already see that there's some inconsistency because the H naught term shows up in the lateral transport, but it does not show up in the vertical fluxes. So this is one problem, as opposed to latent heat, which shows up in lateral transports and shows up as well in the vertical fluxes. So this is consistent. So latent heat is treated consistently, but moisture enthalpy fluxes are not. So we propose a more complete energy budget. And so the energy divergence in the atmosphere is essentially unchanged, but we propose that we also need evaporation and precipitation enthalpy fluxes. And now you see that in all terms the H naught shows up, and as long as mass is conserved, we can just drop the H naught. I will do that now. And so we end up just with Fe and Fp, which depend on precipitation and evaporation temperature. And there's also a term associated with snowfall. So for practical evaluation, it's of course quite cumbersome to get estimates for FP and FE because P and E are usually rather difficult to estimate. But there's another way. We can just consistently remove water vapor enthalpy from the budget. So remove FP and FE, but at the same time, we need to remove it from the lateral atmospheric transports. So we checked the error we make by doing this, and it's actually quite small. So we basically assume that vapor does not change its temperature on its passage through an atmospheric column, and the error is less than 5 watts per square meter locally. And it makes computations substantially easier, of course. So I'm showing results now for this kind of improved energy budget framework. So on the left, you can see again the difference of inferred surface energy fluxes with series plus OA flux. And on the right, you see the differences when we use the improved framework. And so you can see it already from the fields that the differences are much smaller. The RMS values of the differences drop by up to 30–40%. And it's actually quite nice that the RMS values are on the order of 10 watts per square meter, which is quite good for surface energy flux, which is really hard to estimate. I would also like to spend a minute on discussing the surface enthalpy fluxes because they are quite interesting. So their effect is actually quite small compared to the H0 effect I was just discussing, but they have a global mean impact. So what I'm showing on the left is the net effect of precipitation and evaporation enthalpy fluxes. And just look at the global mean. It's a net cooling effect on the surface of 0.7 watts per square meter. And on the right, I put the field showing the effect of snow falling onto the surface, and it has an additional cooling effect of 0.6 watts per square meter. So the sum of these two is 0.3 watts per square meter. And this means that if we want to have just a steady state in the ocean, the net surface energy flux needs to be higher by 1.3 watts per square meter just to balance these two fields. And if we have like an ocean warming, which we do observe, and if this ocean warming is X watts per square meter, the net surface energy flux must be 1.3 plus X watts per square meter. So I mean, this might be an academic note, but I think it has implications for climate models. So to summarize and also to conclude, I hope I could convince you that there's definitely shortcomings in current energy budget formulations. And it's important to note that this is really a purely diagnostic problem, and hence it affects really all reanalysis products. I also showed that we get quite substantial improvement for inferred surface energy fluxes when we use this improved framework. And these inferred surface fluxes also allow for a much cleaner comparison with climate model output. Regarding the surface enthalpy fluxes, I think it would be good to include them in models because the CMIP6 requirements document really explicitly requires these fields to be stored. So I think it would be also good to do that with reanalysis, especially when they are going to be coupled. And I put here also 2 recommendations for archiving of budget fields. So first of all, I think it would be really helpful for the users to archive mass-consistent total energy divergence. And here I mean with mass consistency, I just mean fields conserving dry mass at least. And in addition, it would be good to store the divergence of moisture enthalpy transports so that users can really consistently remove this field from the total energy divergence so that they can use this improved framework. Thanks a lot.
Thank you, Dr. Meyer. Are there any questions? Lassù? Oh, everybody has been convinced by Michael Murray. Oh, okay, two questions.
Yeah, I think this archiving strategy would really help the users, because currently it's really difficult to use the post-processed products that are stored in the archives, and it's quite an effort to store these data, and yeah, okay.
Yeah. Can you comment on what the implications of these surface enthalpy fluxes regarding the CMIP6, where in general the tuning of coupled models?
Yeah, I think this. So I saw several issues coming up over the past month. And I think they all might be related to the neglect of these fluxes. So for example, in the ECMWF's IFS, we see an apparent heat source, so the budget is not closed. And treating moisture, so vapor enthalpy inconsistently might be one reason for that. And for CMIP5 models, it has been shown that the surface energy fluxes and ocean heat content when accumulated, do not agree very well. And so it might also be one reason for that. So I think, especially when doing really coupled models or reanalysis, it's really necessary to have the moisture fluxes not only consistent in terms of mass exchanges, but also in terms of enthalpy exchanges.
Is land surface precipitation and hydrology in MERA2. It will be given by Rolf Reichle from the NASA GSFC. Thank you.
Thank you, and thank you to the organizers for giving me the opportunity to present, and also like to quickly acknowledge my co-authors who are listed here, although with a project like MERA2, you can imagine there's no way you could list everyone who's helped create MERA2, which has really been the challenge. So I just want to look at the land surface. We're back on firm ground, and MERA2 is maybe just a little bit of an outlier in a different sense in what we do with the land surface precipitation, and that's what I wanted to summarize here. So let's first take a step back to MERA, which worked as far as precip is concerned, like your standard reanalysis. You had an atmospheric analysis, so you get the humidity right, et cetera, temperature in the atmosphere, and then you let the GCM work out the precipitation that falls on the land surface, and that this gives you hydrology that's not quite what you want. The precip is hard to model. So that's what we learned with MERA, and we did land-only replay of the land surface called MERA Land, where we used observed precipitation to force the land surface and thereby improve the hydrology. That was the supplementary product to MERA. And for MERA2, we've simply included this analysis, well, this correction to the observed precipitation within the cycling coupled reanalysis system, where coupled, in my case, is land atmosphere. I'm not talking about coupled to the ocean. So the model generates precip within MERA2, and then we correct that precip based on observations before it hits the land surface. So in MERA2, you have two precip fields floating around. One is the model-generated precip, I call it M2H ECM sometimes in the plots, and then the corrected precip that's actually experienced by the land surface. So with this introduction, let me press again. Just briefly, the outline of the talk, I want to talk about the corrections algorithm and the skill of the precipitation, both the model precip and the corrected precip, and then look at the line surface hydrology. I'd like to convince you that things have improved in Mara 2 over and above Mara. So again, take a step back, how this worked in Mara land. The flow chart here is fairly simple. I don't want to bore you with the details, but the important thing to understand with these precip corrections that we do is that this is not a climatological rescaling. We directly insert the precipitation from the observations data set to the extent possible, meaning for Mara land, we use the gauge-based product everywhere, globally, over land. And for each day, and for each half-degree grid cell, we adjust the precipitation that falls onto the land surface to match the one in the observations. And the subdaily variations come from the Mara model precip. This got a lot more complicated in Mara 2, where the flow chart is hard to get through, so I don't want to bore you with it. Two key differences. A gauge-based product everywhere was a little naive in Mara land. There are few gauges at high latitudes, so we recognized that. We decided to back off and not correct the model-based precip at high latitudes. That's tapered into our corrections with that same gauge-based product everywhere over land except in Africa, where you also have very few gauges. Here we fall back to a coarser product, both in time and in space. It's a 5-day, 2.5 degree product. Based on satellite and gauges, so that's a higher quality where you have few gauges. Let me move on. And here's the skill of that corrected precip product on the left against GPCP version 2.2, which is a somewhat independent precipitation product. They take more time. GPCP comes out months after real time. They take great care in correcting gauge errors and so forth, but it's only at a monthly scale, and it comes out far too late for us to keep the reanalysis going, which is one of the main reasons why we chose the CPC products, which come out fairly close to real time. But we're doing quite well against that monthly product, so our corrected precip looks roughly like what we want it to look like. There are a few areas where it's not quite as good, but those are areas where there are few observations to begin with. Who knows whether GPCP is great? This is the correlation. So with the little precip you get in the Sahara Desert, you don't know what the correlation really means. On the right, you see the difference in skill between the corrected precip in Mara 2 and the precip that's generated by the model. And this is another reason why we want to do the corrections. Here, the average increase in the correlation is about 0.1, so we're obviously doing something right with these corrections if GPCP is the true reference here. And I think that's about the best you can do at this point. Let's see. There's, of course, not all is well. If you look closely, squint a little bit, you see a dark blue spot in Myanmar. We've traced that back to an error in a gauge product that we used to correct for many years. The reporting there was messed up. It ended up in the CPC product that we imposed, and sure enough, we see problems there. So this just happens. We hope that in the next iteration, we'll get a cleaner precipitation product to work with. If we compare the skill of the Mara 2 corrected precip to that we did for Mara land, and remember that was only CPCU everywhere, we see differences, of course, in those two places at high latitudes and in Africa. High latitudes is a mixed bag. We didn't make anything worse by backing off the gauge-based product and inserting our model-based precip at the high latitudes. We clearly improved over Africa by using the CMAP coarser product relative to the gauge-based product that was based on almost no gauges in Africa. If you do corrections with observations, you have to worry about observing system impacts in reanalysis. That's not a new thing, except in our case now we look at gauge-based precipitation products. This is precip traces over eastern US. We have three lines that match very closely. The gray line is the GPCP reference, and then the blue line is the model-based precip from Mara 2. The red line is the corrected precip from Mara 2. These are annual totals. all matches very well, but you see that over the years you have different numbers of gauges, so the observing system clearly changes. It doesn't seem to impact the precipitation much. So eastern US, you were hoping to get away with that. Not quite the same in the Amazon, where around 2004, we drop off a cliff in the number of gauges underlying this product. I think this is when they went from a retrospective processing to their real-time processing in the CPCU product. And you can clearly see in the red line here that we lose a bunch of the precipitation. So this is another hit you have to take. But I wouldn't let that stop us from doing the corrections, because there are other issues with the model-based precip. For example, here in Central Africa, you also have these undulations in the number of gauges that are used, but you clearly see in the model-based precip here a change in the climate that is timed with the insertion of the AMSU in the atmospheric analysis. So not using the gauge-based precip because of these problems doesn't really help you, because you just trade them for other problems elsewhere. So on balance, you still have to worry about observing system impacts in these gauge products, but I don't think that we're doing any worse. We looked at the diurnal cycle, and as I said earlier, the sub-daily variations in the precip that the land experiences are inherited from MERA. We compared that to TRIM, and this is the amplitude of the diurnal cycle on top from TRIM, and from the MERA2 corrected precip, it matches reasonably well. Now, diurnal cycle amplitude is fairly closely tied, not independent of the magnitude of precipitation. And I think that's the main reason why we get this reasonably well. The model-based precip from MERA2 doesn't have quite that right amplitude yet, which is another reason why it's good to do the corrections. But if you look at the phase, for example, over the central US, you have the typical nighttime precipitation here in local time. MERA tended to rain midday, sort of early afternoon, between noon and 2 p.m. local time, and that's just what we inherited. That's not something we could fix in this case. And the MERA2 HECM has more realistic variations in the peak of the diurnal cycle, but it's not like MERA2 model-generated precip matches the observations all that well. So with this, I'll touch on the land surface hydrology. What does this enhanced precip buy us in terms of skill at the land surface? First comparison is at very coarse scales. Those monthly large-scale terrestrial water storage variations from GRACE that we heard about yesterday. You see skill is reasonably good for MERA2 TWS terrestrial water storage versus GRACE. And on the right, you see the improvements on top, over and above MERA in terms of the correlation, and in the bottom, over and above MERA land. You can see here clearly we inherited that Myanmar precip gauge problem, but by and large, we're improving by about 0.1 in the correlation again. And in MERA land, we're clearly improving at the high latitudes, so another reason not to use the gauge-based product at high latitudes. We're also improving over Africa. So consistent story, what we gain in precipitation skill, we essentially just transferred to the water storage. There are other metrics, I forgot to mention that earlier. We looked at anomaly time series, we looked at RMSEs. Story is generally similar, so I don't want to bore you with too many different metrics. Soil moisture is also improved. Here we're comparing also to ERA interim land. So we have two products that are land-only reanalyses. And the story is essentially that we're clearly better in MERA2 than we were in MERA. And we're on a par or even slightly better than the land-only products in soil moisture. In streamflow, big busy graph, but the story is the same. We're improving the runoff skill in these large basins. So one more thing for snow, that's a sort of mixed bag, more difficult story. Here's the bias versus what we call a reference product, the CMC product, sort of from the global snow products perspective, perhaps the state of the art still. We see biases in MERA2, wet biases at the highest latitudes. There's this large area of very dry bias. By and large, in the global average, we're almost unbiased, but we're slightly overestimating the snow water equivalent. One thing I just want to relate to you. In MARA2, we changed a snow model parameter in the snow depletion curve, which ultimately leads to an underestimation of the snow cover area. So the model works by piling snow into higher piles before it gets spread sideways. So a snow cover fraction underestimation in MARA2 relative to mode is only superficially inconsistent with that high bias or slightly high bias in the snow water equivalent. It's just a quirk, really. This could be rescaled if you really needed to use snow cover fraction or snow cover area for something. If you compare that to the biases in the other reanalyses, MARA land, MARA and ERA interim land, MARA2 doesn't stand out as particularly bad. For some reason, MARA worked really well at high latitudes and precip amounts. We haven't been able to reproduce that. The really dry bias here in Asia is to be taken with a grain of salt, because this is the distance from observation in the CMC reference product that we're comparing to. So essentially, this is telling you there's nothing to compare to in this area. So that's why you should probably pay a little more attention to the higher latitude biases. But even in ERA interim land, you have real problems there in this area. So the one question that we would have really liked to answer is what really is the aggregate impact of the precipitation corrections within the cycling system on the rest of the reanalysis. And it's very, very difficult to do without rerunning the reanalysis, leaving out the precip correction. So we don't have that clean control. So we looked at a couple of things, and one thing that is even simpler to answer is what is the consistency between the land surface forcing fields in MARA2 as opposed to MARA land? Remember, in MARA land, we took the precip from the observations, but we took the T2 meter or the air radiation, et cetera, from MARA, and they weren't always consistent, and that's sort of expressed here in low negative correlations where the forcings are inconsistent. And a lot of people use reanalyses to force the land surface models and do their own investigations. With MARA2, this is much improved, because here the correlation between, and this is correlation between 4-day average precipitation and the subsequent T-air, sort of how does the T-air respond to a recent precip event, is much more realistic. So that's built in, that's nice. We looked at this also at more monthly timescales and compared that same metric, antecedent precip to subsequent T2 meter, between the model precip and the corrected precip. If you difference that, that gives you the sensitivity of the T2 meter to your precipitation corrections. It's one sort of attempt at measuring this. And what's nice about it is that this compares reasonably well to the skill improvement in T2 meter versus completely independent reference data. In this case, the CRU data. So this is the difference between the skill in MARA2 and in MARA for air temperature. And a lot of these areas, the Sahel, for example, or Mexico, overlap. So we basically can suggest that the precip corrections did help improve T2 meters. And with this, I'll just briefly go through the summary slide. We have the precip corrections in MARA2 in the cycling system, so there's no need to do a MARA2 land at this point until we find something else that's wrong. We won't plan for doing that. It's an extension from the MARA land system, and overall we improved the precipitation and the hydrology, and we see a positive impact and also a more consistent set of surface meteorological forcings that can be used in offline studies and improve T2 meter simulations. The thing that's really important to understand here is, of course, this critically depends on having precipitation observations at the global scale with sufficient latency so you can extend these reanalysis products in quasi-near real time, sort of within a couple of weeks. And there are very few products that fit the bill, and those are not necessarily the best products that could be done. So there's a bit of a need for better precipitation observation products for this type of study. Thank you.
Thank you very much. Are there any questions?
Joaquin Muñoz, ECMWF. Thanks, Rolf. It's a very nice presentation. You just offered 2-meter temperature, but I wonder if you have an estimation of the improvement you get when you correct precipitation. in the hydrological variables compared to the case that that you don't correct precipitation? Do you have an estimation of that?
I mean, not beyond what I showed. We don't have that control run, that clean control run, because it would mean we have to rerun MERA 2 without those precip corrections. That one change would be really expensive to do for just investigating this one question, so I don't really know. We can compare to MERA land and MERA, but it's essentially undoable for resource reasons.
Clemens Schingsackle, ETH Zurich. You showed the different time series, or different series of precipitation from GPCP for the model precipitation and the corrected one. And first, the corrected one didn't match the CPCP correction all the time, or the GPCP values all the time, and sometimes it even was further away than the model precipitation. Why is that?
I mean, the product we use is a CPC NOAA Climate Prediction Center precipitation analysis that's not identical to GPCP. They use different sets of gauges and different corrections for undercatch, different processing. It's not the same product, so we think the GPC product is the better product, more carefully done, but it's not available in the latency that we want it at, so we just need to make sure that the gauge product or the satellite gauge product that we use is close enough to GPCP. Now, it is true that it's not always closer to, the corrected product's not always closer to GPCP than the GCM-generated precipitation, but on balance, I think it's clearly much closer based on the variety of metrics that we did show. So sometimes it's not working out right, but you can't get it right all the time, unfortunately. Another question?
I understand that MERA 2 is more coupled than MERA because you use a coupled model. Do you have any plans for the next generation of the MERA reanalysis to implement a land data assimilation, and how much coupled it will be?
I mean, we do have plans to include, say, a snow and soil moisture analysis in the next reanalysis. We're working on it. I will have to say, though, that with some question marks surrounding the early years of, say, the CCI soil moisture product, the quality thereof, the precip corrections, I think, are still going to be instrumental in the earlier years in particular, because the quality of the soil moisture product as you go back in time just decreases dramatically. We really only have good soil moisture products starting with, perhaps with ASCAT and AMSRE, but not before that, which would be the mid-90s to early 2000s. I guess one other way to look at it, I want to add that these precip corrections are in some ways just a poor man's soil moisture analysis.
Jiří from GSAT, thanks for a good presentation. And I was wondering about the snow cover. You were showing MERA 2 overestimates snow depth in high latitude and underestimates in the lower latitude. So do you have any reason why this could be?
I mean, it is precipitation based, I guess, and also the radiation isn't perfect, so our snow will melt too early or too late. It's a combination of factors between the forcing, the precipitation, and the other force in the radiation, and just imperfections in the snow model. It's a very simple snow model, 3 layers. It has a little bit of densification and stuff, but it's not really a high quality snow physics model. You can't afford to do that in a global reanalysis.
Thank you very much. And now I would like to invite...
Okay, so I would like to thank all the chairs and the speakers today. So today we finished the part on methods. So we've had the posters on methods as well. So this part's behind us now. We're into the evaluation. It will continue tomorrow. And for the rest of the day, we'll have 1 keynote. So you remember the program is structured with 5 topics, and we have also cross talks, keynotes. So this one will be on a perspective from the atmosphere for the future Earth system reanalyses. Gail Compo, please. Thank you.
I'd really like to thank the Scientific Organizing Committee for giving me this opportunity to talk with you all. I'm on the Scientific Organizing Committee, so that's kind of bad form in my opinion, but I tried to get out of this. They said no. So what I'm beginning with here there it is. You just have to be patient. What I'm beginning with here is an animation of the weather in 1881. The current day is May. It's the 24th, the 25th. You can see a lot of caterpillars moving around. Those are ships. They're taking surface pressure observations. The not moving ships, the slow weather platforms, are stations. The vectors here are our reanalysis of the 10-meter wind. This is from the 20th century reanalysis. This is a test version. You can't get this one very easily yet. Coming soon. The red is where it's warm. The blue vectors are where it's colder. The dark gray is where it's precipitating. The light gray is what our colleague Philip Brohan calls the fog of ignorance. This is where the ensemble, the 56 members in this case, are so far apart that they cannot be distinguished from climatology. And you can see as the caterpillars move through the fog, as our ships move through, they clear the fog, they bring knowledge. And in this particular case of 1881, there we go. We're going to pause for just a second. So we've chosen this because this red dot here, this represents the ship, the USS Jeannette, which was an Arctic exploration mission. It launched in 1879 from San Francisco, went up the bay, went all the way up, went through the strait, started taking scientific observations, and then it got stuck in the ice, frozen solid. And it actually became the first drifting ice station. It's 1881. They've been drifting since 1879 at this point, right there. This ship is actually the core wind. They're looking for them. They're trying to figure out what happened to them. The volunteers of oldweather.org have digitized this ship. They've digitized the observations from this ship. We'll see one more. Here's the Rogers getting ready to leave to also go look for the Jeannette. So it's our good fortune that we have these additional observations in the Arctic to reduce the fog. And the data assimilation system, when it has these observations, can react and tell us, we have more knowledge here about the weather than we did a few days ago, even. We can estimate the uncertainty. Here in the Atlantic, where things are pretty rich, we have a pretty good estimate of what's happening to the weather, even in 1881. And as we advance to, there we go. As we advance in time, you'll see it's to be hurricane season. The Jeannette, unfortunately, is going to sink. But we have the data, and that in itself is a miracle. The men on the ship abandoned ship. They knew it was going to sink. They could hear the timbers crashing. And they divided up into three parties because they knew they could not survive all together. And the captain kept the logbook. And his party got on a small island, and they actually all started to starve to death. And he sent his two strongest men to cross the ice on foot. And they actually ran into Chief Engineer Melville, a cousin to Herman Melville, who wrote Moby Dick. And they came back to where the captain and his part of the crew were. They had all died. There's a very famous cairn that's there and also reproduced at the U.S. Naval Academy. And Chief Engineer Melville wanted to go find more survivors, so he sent the logbook. It was given to couriers in Russia who got trapped in a flood. And then eventually, by about 1886, the logbook makes it to the US National Archives, where it sat, pretty much unlooked at, until the Old Weather Project, led by Kevin Wood and Philip Brohan and Mark Milan with the National Archives, got it out, imaged it, and volunteers typed the numbers in, and you're seeing the results of all their typings as they create knowledge of the weather. The other bit that I want to show you for this time period, you can see we're in hurricane season, and there's one. That one doesn't do much damage. Here's the next one. It's going into Georgia. Just killed 700 people in that time period. We didn't have satellites. But we can now put in context, with some uncertainty, a lot of uncertainty, what was happening across the century. So that's the future of reanalysis that I want to discuss, after making one additional point about just how valuable these observations are. Driving is really hard. Pause. There we go. So here's an artist rendering of the men carrying the logbook in that chest, actually. DeLong is the captain. They carry it through a mile of broken ice. They could have left that logbook there. This is hard. But they were on a scientific expedition. If they lost these pages, then everything they had done would have been in vain. And I feel that we owe it to these people, to all the expeditions, to all the people who took all those observations, to do the absolute best we can with their observations, and thinking about future society to make sure that we connect those 19th century observations to our own experiment in changing the atmospheric composition. And here's the head of NOAA at the time, Jane Lubchenco, getting that logbook out before it got imaged. And actually, they found some flora that no one realized would have been growing at the time that was in the logbook itself. The Jeannette also, here's the picture of it being crushed. The Jeannette also provided, even in its destruction, scientific data. Because when Nansen arrived in Greenland, he found the wreckage of the Jeannette in Greenland. And yet I showed you where it sank. So Nansen deduced the ice must be flowing. It's the first time someone realized that the ice was a dynamic field. So even in its destruction, the Jeannette served a scientific purpose. That was backwards, or forwards. Left is forwards. Okay, so does global atmospheric reanalysis have a future? I've rephrased the question. Do we need to keep doing this? Retrospective analysis, reanalysis over and over and over again? That's what I want to be thinking about for the next few minutes. So I'd like to thank all my co-authors on this presentation. A lot of the philosophical, almost existential ideas that we'll be discussing are really coming from my colleague Prashant Sardeshmukh, senior colleague, who I'm very glad to have here. Jeff Whitaker and Laura Slavinsky, who's also here today. Aaron Wong, Chesley McCall, who was actually making a plot for this talk at 11 o'clock Colorado time last night. Philip Brohan, who, among other things, made the excellent animations that you'll see. And Rob Allen at the UK Met Office, and also the head of the Atmospheric Circulation Reconstructions Over the Earth Initiative. That's helped to bring together so much data for the 19th century and into the 20th century. So the other aspect that I want to think about for a minute is what we're trying to do with reanalysis. And I think it was great to see some of the paleo reanalyses and to sort of stretch the word a little bit. What do we mean? So this is from the UK Met Office. It's a little kind of an old figure now. So we have long paleoclimate reconstructions. We have our climate model simulations. And really the answer didn't change much, to be honest, between CMIP3 shown here and the different projections and CMIP5, and I'm afraid CMIP6 really isn't going to have a different answer. As far as the models know, if we change the composition of the atmosphere and make it less transparent to infrared radiation, the planet warms. instrumental observations represent a thin wire that connects the paleo and our projections. And so we need to do our utmost also, if this is right, to make sure we understand the strengths and limitations of those models. So there's a paper that we've been working on for a while. Any of my co-authors in the audience on what are global climate reanalyses for, needs, uses, and prospects. The paper's not dead. It's been a while since we talked. So they'll be seeing some results for the first time as well. So what are the top 5? 5 was the number of the week. What are the top 5 scientific reasons for global climate reanalysis? And I'm drawing a distinction here between climate reanalysis and the reanalysis that you want as an initial condition to make a reforecast to improve your forecast system. That, for me, is a little separate from what I'm going to talk about here. We want to create as long as possible. And that may be different depending on your interest. Long might be for the stratosphere or even higher, the ionosphere. Long might be just a few years, a few decades. For the surface, I think we can go a lot further. For the troposphere, I think we can go a lot further. So we want long, dynamically consistent record of the mean climate. We need the variability and the trends. We want to be able to see individual extreme weather and climate events in their long-term context. Every time there's an extreme weather event right now, USA Today or some other newspaper gets a scientist who has a PhD to say, this is evidence of global warming. I think we can make those statements either more or less rigorously than they're being made. I think that should at least be the goal. So we want to assess the significance of any trends in the mean, also in the variability. Is the distribution changing? Is its shape changing? In the statistics of extremes. We want to be able to verify and validate climate model simulations of the mean climate, variability, and the trends. Now, to this audience, this may seem almost obvious, but there is a tremendous prejudice in our climate modeling community against using reanalysis. It's almost a bad word. So I think we need to be considering, can we use it? Is it good enough? Is it fit for purpose for verifying and validating climate models? And I was very pleased with one of the last speakers because we want to be able to improve climate models through intercomparisons of model and reanalysis budgets. And we saw a nice talk on energy and how to consider those budgets. It's definitely a goal. So here is a curve that we've seen many, many times, but the sources that I'm showing here are a little different. So the fuchsia curve with the 2 sigma shading is from the 20th century reanalysis. This has only assimilated surface pressure observations, but the sea surface temperatures are specified. And here I'm showing you the global average 2-meter air temperature, complete global average. Nothing has been left out. It is currently only from reanalysis can we get 90 north to 90 south, nothing missing fields. Nobody else can do that right now. Coming soon, perhaps from Eustis, but not yet. This is back to 1873. In the thick black curve with the gray shading is the last millennium reanalysis that was introduced earlier. This is coming from paleoproxies with no cycling. The level of agreement is actually quite high. And then the 2 blue curves are the SARA 20C and ERA 20C systems. The thicker blue happens to be the coupled newer system, and it's the mean of 10 ensemble members. We have too many shading ranges here, so I'm not showing its range. And then we start to get to the modern era. The purples are the JRA 55 and JRA 55 conventional only, no satellite data. And these are actually observed because JRA does a separate offline 2-meter air temperature analysis. It doesn't cycle, but every 6 hours there's all the synoptic temperatures are used. So this is to me, about the best you can actually do every single 6 hours. And it's in this sort of spaghetti mess. And then we've got ERA interim and CFSR, and you can see the trend lines that we then extended. And the dark gray curve here with the very light gray shading, 16 CMIP5 models extending over the period. So you can see the range in response to the volcanoes here. The reanalyses, even the paleoproxy, much better constrained than the models. And aside from this peculiar interruption in international collaboration, as my Swiss colleague Stefan Bronnemann called it one time, we call it World War II, in 20 CR being quite an anomaly. The agreement here is quite good in trends, in variability. And so the last bit then is, if they're good enough, can we say that the reanalyses are showing that the CMIP5 really is too warm for the end period, even outside of its range? But the surface isn't what reanalysis is considered to do best. It's the upper air. So here I'm showing you now the zonal mean, zonal wind annual anomalies, 30 north to 50 north. So the combined jet from the 8 different reanalyses and from the 16 CMIP models that we're considering here in the light gray shading that, I apologize, it's very hard to see on this screen. And what you can see immediately is that, if anything, the northern hemisphere jet has been strengthening over the long-term period from these very differently constructed data sets. And this recent weakening is really a decadal, multi-decadal fluctuation when considered in the long-term historical context, if we think we can trust these values. So I'm asserting there's enough agreement here, there's enough maturity, we need to keep looking at it, that we can trust these values. We can tell our colleagues in the IPCC, CMIP6, you can really start to look at this. This is what you're aiming for if there's a radiatively forced signal in this. We also want to look at maps. So I've heard many times recently, both at this conference and other climate conferences, that we're now seeing the emerging signal of the change in atmospheric composition. Global warming is emerging in changing everything. So on the right-hand side is the mean 250 millibar zonal wind change from the most recent period through 2010. We have several reanalyses that stop in 2010, minus 1980 to 1994. So we have several that start in 1980. MERA 2 defines that date for us here. So this is the pattern of the mean of all of them. And then the black lines here are one indication of the zonal mean jet, of the jet at each point, rather. So this is the 42 meter per second contour, just to illustrate that what we see, say, in the Pacific is a slight northward shift of the jet here, a weakening of the jet, but in the Atlantic we have a weakening of the jet and a strengthening of the jet to the south. In the southern hemisphere, it's a more consistent strengthening of the jet poleward. CMIP5 has the opposite signal. It's a weaker signal, the mean of the 16. Completely the opposite here. There's a hint that something in the Atlantic is similar. The southern hemisphere actually looks pretty good, which is surprising because that's where you'd say that maybe the reanalyses are weaker there in general. But I've seen some results that would suggest that this is actually an ozone-induced change, not greenhouse gases. And if we look at the pattern, so how well do these 8 reanalyses agree? So this is a Taylor diagram. The distance here we've referenced to the mean of the 8 reanalyses. Each dot represents in its angle the correlation, so across the top. So here's a correlation of 0.9, this angle. And then the distance is do the amplitudes agree, and the radial distance out is the root mean square. It's a beautiful geometry. So the red curve here is where 90% of the reanalyses are lying. So the reanalyses, including the surface input reanalyses, are really agreeing quite well. There is one outlier in this field, CFSR, it turns out. This is where the CMIP5 models are. Here's the ensemble mean. It's almost exactly a correlation of 0. In this recent change, there is no radiatively forced signal at all. And I think given the level of agreement of the reanalyses with their different changes, surface input, the conventional input, the JRA55C, ends up being very powerful in this because it's only assimilating the radiosondes. So we know that this change is not coming from some satellite jump. So I think we can start to be confident in at least the tropospheric fields, the details of the fields, decadal differences to compare to the models. So I think we're getting somewhere on that top 5 list for what is reanalysis good for. Now I'd like to reflect for a few minutes on what are the top 5 parts of reanalysis. We've been talking about these in various configurations, and I'd like to take a few minutes to go through them. So the first is the observations. Without the observations, you're doing a simulation. It's not a reanalysis. But if you have some observations, even sparse, we can call it a reanalysis. Paleo, we still need to discuss that. We need a model generating the first guess. We need some algorithms that are going to combine the observations and the first guess. We haven't talked so much about item 4 here, the computing. At the discussion panel last night, there was a mention that numerical weather prediction used to have the best computers in the world. And I think it's time to start to push again that, particularly for reanalysis, if we're going to make trillion-dollar decisions about how society is going to be organized, then we need to have the best resources available to compute these fields. The last component of reanalysis, we cannot keep this to ourselves on our server. We have to distribute the fields. So each reanalysis center is doing this, the National Center for Atmospheric Research, the British CETA, I don't remember what that stands for, they changed their acronym relatively recently, but really great distribution. We also have to have a way to support the users, and that's why I've put the reanalyses.org logo here. So this is a hybrid wiki blog anyone can join. If the Wi-Fi were faster, I'd suggest that you log in, set up an account, make sure you give a real affiliation when you set up your account, otherwise you get treated as spam. Kathy Smith, who's has a poster on it tomorrow. Did you already put the poster? No, yeah, posters tomorrow. Talk about this more. Everyone here could contribute, ask questions, post things, post your results, as we try to expand the knowledge base, if you will, about reanalysis. That's what this is for. There's also the Climate Data Guide at NCAR, and I found the KNMI Climate Explorer is extremely useful for also looking at data. There are additional tools on reanalyses.org that you can get to. So now I want to just look at a couple of these aspects of the parts of reanalysis. We've already touched some on the observations, but I want to say, with the observations, just how far can we go? I liked Patrick Lawayo's, what are the most frequently asked questions? So for 20CR, the most frequently asked question is, just how far can you go back? Now, almost exactly 4 years ago, Stefan Bronnemann and Philip Brohan, we were in Lisbon, which has good port. I happen to like port. So they took me to a bar. Stefan said, Gil, do you know that in a few years, it'll be the 200th anniversary of the eruption of Tambora, the largest volcanic eruption in recorded history, recorded because an Englishman saw it. In 20CR, do Tambora and the year without a summer, 1816? I said, no, there aren't any observations. He bought me a glass of port. And then he showed me a map of the observations that we could have if they were digitized over Europe and a few over the US. He said, what if you had this scattering of observations? I said, no, it's not enough. Philip bought me a glass of port. And I said, well, when could you have those observations? And he said in time, not too long from now. I said, let's try. 2 glasses of port. That's the cost of your reanalysis. I clicked. And lost. Not advancing. It was a helpful beep. I'm going to not click. I'm going to let the gentleman in the back click. Other way. Yes, okay. So, this is the 1815 implementation of the ensemble filter used in 20CR version 2. So, we've learned a lot about the ensemble Kalman filter already, so we know that the K matrix, the Kalman gain, is changing both with the atmospheric flow and the observation network, and it's changing every 6 hours. We're still using our 56-member ensemble. We're prescribing climatological sea surface temperatures. We don't have an estimate. We didn't. We might use Michael Mann's in the future, I suppose. From the Kobe SST2, the 1861 to 1890 averages of sea surface temperature and sea ice concentration. And this is at T62, so 200 kilometers, and it's only 28 levels in the vertical. But this experimental version of the NSEP global forecast system was the first version that could include time-varying CO2. We have an 11-year repeating solar cycle, and we can include the stratospheric aerosols. So we've done 2 experiments that I'll show you, one where we specify no aerosols, and one where we specify the volcanic aerosols according to Crowley. We've actually run every 5th year, producing in parallel through 1816, 1846. So we have a new data set. Our colleague Ben Geis actually has used those to force an ocean model starting in 1815. That's the simple ocean data assimilation with sparse input, version 3 that you could get if you're interested in that. And I appreciated the speaker who said that their paper was in process because it keeps getting rejected. So this paper that we submitted, it's in discussion. 2016. It turns out once you put a paper into the open discussion journals, you can't take it back. And every other journal considers it published. The reviewers didn't have any problem with this paper. They just wanted a different paper. So we said no. So it's kind of a gray literature reference. I think I'm too slow at moving along. All right. Well, no, I just want to see if it would move. There we go. Okay, so the same fog of ignorance where we don't know what's happening. The same golden dots where we have observations. Now you can see the sea level pressure contours and the temperature colors in Philip's beautiful animation here of the weather in 1816, the year without a summer. And these almost look like sensible weather maps. They're kind of really smooth because it's an ensemble of 56 members. If you look at the individual members, which you can get to on Philip's Vimeo channel, each one individually looks like a regular weather map, but when you add them together, all 56, they get kind of smooth. But the individual variations are there. So you can see we just have no clue about what's happening around here. New Orleans has a station. There's some here in the northeast US and in Canada. And Europe, actually, this is the map that Stefan showed me. They didn't get all the stations digitized, but about half of them, actually. There's even more here. Here's a ship, English East India Company, dutifully taking observations. We can actually start to reconstruct the weather 200 years ago. And the weather variations, this is kind of a busy plot. The weather variations are actually timed correctly. So we're assimilating sea level pressure from London, so it's no surprise that the 56 members, the purple here, agree really well with the station observations that we assimilated. At London, the data assimilation system works, like we've talked about several times today, so the correlation there is 0.94. But the air temperature is entirely independent, and that's pretty decent correlation for daily data, 0.55. One of the things that was sort of surprising is that 1816 here doesn't appear particularly anomalous in the 20CR reconstruction of this period, or in the London series at least. The year without a summer, this great cold spell, was part of actually a larger cold spell that Stefan was describing, and we're seeing that some. So this is being done just with 4 North American stations and 10 European stations and about 10 ship obs per day. We could get somewhere between 2 to 4 times more observations. This is one aspect of the observations part of reanalysis that I wanted to emphasize. So there's a lot more data that can be rescued that we can use at the surface, in profiles, from the satellites even. But we do get a cold signal. And that cold signal we can attribute. We can use reanalysis for attribution. We can attribute it to the aerosols, because when we run the reanalysis with no aerosols, the pressure observations alone know about the temperature, so you get a cold anomaly. But if you prescribe the aerosols as well, you get it even colder and closer to the observations. I'd like to move 200 years into the future, from 1816 to 2016. Large El Nino was going on. The National Oceanic and Atmospheric Administration said, we need to do something. There's an El Nino. Decided to go measure it. There actually had never been a field campaign active in the heart of El Nino. So here's the El Nino event of January through March 2016, schematically, and a series of observation measurement types were deployed. The ship Ronald H. Brown, the NOAA Gulfstream 4, flew out of Hawaii every other day or so and dropped about 30 dropsondes on its flights, going down to the equator around Christmas Island. At Christmas Island, we had upsondes twice a day, and the NASA Global Hawk also flew some missions. So we did a reanalysis. Now, when you look at the observing system, the modern observing system, these are the observation locations over the period 14th of February to 7 March 2016. And the pink are where the El Nino Rapid Response Field Campaign took its observations from the various platforms. The aircraft, the station launching upsondes, and the ship actually launched 8 times a day upsondes as well, and that's the track of it. It happened to be already going out to 10 the buoys, so we put a couple of really hardy colleagues on it, and they launched 8 times a day. Turns out that's really hard from a ship. Not all the launches got in. And almost all this data, you're seeing it here because it was actually sent in real time. And the weather services around the world had it to assimilate. ECMWF received it, NCEP received it. What did it do? What's the value of observations? This is the other aspect in the modern observing system. You can see there's a gap in the mid-troposphere in the tropics. Did it make a difference? So we've done, this is a paper that our colleague Aaron Wong, Jiwon Wong is leading at the Physical Sciences Division in Ceres. We've done a series of sensitivity experiments using the operational NCEP system, not operational at the time of the campaign. This is a reanalysis, but for a very short period, 2 months. And we're looking at the sensitivities of the global forecast system at a reduced resolution. We couldn't afford to run the fully operational. Those experiments were actually done by our colleagues at the Environmental Modeling Center. So we did the reanalysis, and then we initialized forecast, 80-member ensemble forecasts, because we're doing the full 80-member ensemble hybrid system. Every 12 hours, 80-member ensemble forecast over this period. So we have a total of 100 forecast cases, 80-member ensemble, so there are 8,000 forecasts that we can look at. So that what we call the control are the 7-day forecasts. So our initial conditions assimilated all the available observations, including the additional ENRR observations. that if you're thinking dynamically, wind observations in the tropics, in the most sensitive region for forcing global, this is going to have an impact. That was my hypothesis. Spoiler alert, I was wrong. Initial conditions, we're using the hybrid 40 ENVAR that was introduced earlier, and the forecast model includes stochastic parameterizations. This is the Buitza et al., 1998, and updates the stochastic perturbed parameterization tendency that's been implemented by our colleague Phil Péjean and Jeff Whitaker. So the forecast model has this kind of representation of model error. And then we're going to compare that control to what do you want to put your money on as we look to improve the systems. So we're going to deny, in the initial conditions, we're going to deny those special dropsons and radiosons. We're going to have fewer observations. We're going to use a different algorithm. We're going to do pure ENKF, not the hybrid, and get new initial conditions and also rerun forecasts. And we're going to, from the control, we're going to also rerun the model, an additional set of 80-member ensemble every 12 hours, and turn off those stochastic parameterizations. What do you want to put your money on for what's going to have the biggest impact? What's going to make a difference to the forecasts? And a lead for data assimilation, like 12 hours, and a lead for a forecast, say the 7-day forecast. Which of these is going to have the biggest impact? What's going to make the difference? Observations, the algorithm, the model. And for truth, we're going to be verifying against, for precipitation, satellite-based observations, and we're going to use the control analysis for the other variables, and we can have a discussion about what's truth when you're using the control analysis. So think about, make your wager, note it down. Which one has the biggest impact? Now you have to be able to see that. So here I'm showing you 6 different variables. The global root mean square error for the top 5, the error is with respect to the control analysis. Hybrid 40 ENVAR using all the observations. And then the lower one, this is the one that in a sense seems like the most truth, the independent precipitation observations. And we've got here 4 different curves. So the gray thick curve in all of these, 200 millibar heights, 200 millibar vorticity, the gradients in the heights, 2 meter air temperature, 500 millibar vertical velocity, this is a tough quantity, precipitable water, and precipitation. The gray curve in all of them is the growth of the root mean square error as a function of forecast time out to 7 days, 168 hours. The blue dashed curve is where we denied the special ENRR observations, this collection of dropsons and radiosons. So other than, so if you're above the gray curve, you're worse. The degradation resulted in worse forecast scores. You can see that denying the observations has almost no discernible effect at all. So it turns out if we go to just looking over the continental United States, at days 3 to 4, you can see an effect which made NOAA program managers really happy. But by and large, you definitely have to say this is a process data set. That's the impact it's going to have, is to be able to look more at what happens with convection. Having a whole bunch of additional observations in the plethora of observations we already have doesn't make that much difference, at least this set. Now, when we use the ENKF only algorithm, the dotted green here is discernibly worse at the short ranges. And then at the long ranges, it actually pretty much converges for all variables. And if we look at the precipitation, which is a clear arbitrator, by 7 days, you can't tell the difference in your 7-day forecast between having initialized with the hybrid and having initialized with the ENKF. But at the shorter ranges, the ENKF is worse, and we'll discuss why in a minute. The last one is having the no stochastic parameterizations, using the purely deterministic model and just letting the chaos of the atmosphere spread apart your 80-member ensemble. Those stochastic parameterizations, once we're outside of the first 12 hours, make a tremendous difference. So I'll be telling my junior colleagues, work on algorithms, work on model improvement. That's what's going to make the difference. We look at a map, 12-hour RMS forecast error of the control compared to the GPM, Global Precipitation Measurement Mission, observations during that period. Here's the impact of using the hybrid instead of the ENKF-DA. So if it's blue, that means that the hybrid's better. The control is better. Having everything was good. So you can see, even at 12 hours for precipitation, by and large, this is blue. Having the hybrid gave you a benefit than the pure ENKF. Including the observations, these extra observations that were in here is pretty much a modeled mixed bag. And the stochastic parameterization really doesn't make a difference. In just doing a forecast, this isn't cycled. The control has the cycled stochastic parameterization already. So if we just make a new forecast without the stochastic parameterization, we can't really tell the difference. But go to Hey, thank you. Day 7. Thank you. 7-day forecast map. So here's the RMS of the control. Impact of hybrid instead of having the hybrid instead of the ENKF. This is where they've converged. That initial condition, the details of the initial condition didn't matter so much for your 7-day forecast. Having the ENR observations, definitely a mixed bag. That stochastic parameterization has a huge impact. Having that representation of model uncertainty, of model error, including that. It's not just increasing spread, which is what it was designed to do. It actually is having an impact on the mean root mean square error. Unambiguously positive impact. So why didn't the ENKF perform as well as the hybrid 40 ENVAR? So in our implementation of the ENKF, this seems like a gory detail, but it's actually really important. The vertical covariance localization of the satellite data is not as good as what's in NCEP's operational system. The hybrid also gives you a balance constraint on the increment that's not in the ENKF. And we could use more ensemble members. That would be another way to try to, we have 80 members right now, but we need to reduce that sampling uncertainty. Now, why did the stochastic parameterization help lower the root mean square error? It's doing more than just increasing the spread. That comes as a surprise. It was supposed to increase the spread and make the spread closer to the error. It actually is lowering the error as well. So there's a state-dependent, a multiplicative noise effect that's coming. It means that improving the models, representing the model error, is crucial to improving the forecasts, and it implies that it's a crucial aspect of improving our data assimilation and improving our reanalyses. So there were two other aspects that I just wanted to touch on. This is the future, but the future is practically now. Computing. I'm asserting we should have the best computers in the world. The problems that we're addressing are crucial to the planet. And the best computers in the world are coming. Quantum computing. So qubits, instead of having a bit, 0 and 1, you can now do a superposition between 0 and 1. And that means every time you double the number of qubits, you're exponentially increasing your computing power. Google is at 2 to the 49 qubits. That's a really big number. To break every single encryption code that's known, you need 2 to the 50. That's it. You need 50 qubits, and they're almost there. So the governments of the world are actually quaking. But it turns out that quantum computing, this particular design of a computer, isn't good for everything. And as far as I understand, it's terrible for a semi-Lagrangian implicit time-stepping scheme, but it's fabulous for optimization problems. And when I read that the other day in the Wall Street Journal, I said, ooh, variational problems are an optimization. ENKF isn't, but variational is. All of a sudden, I'm more interested in 4DR than I used to be. So we need to start thinking about having part of the data assimilation on a quantum computer, having the data assimilation on a quantum computer, and then the part that we can't do on the quantum computer, we need to do with a regular computer. But it may be that with artificial intelligence, we could emulate the model, and the quantum computers can do really well running deep learning. That's the other thing that they're being sold as. So this is part of the future. The other part of the future is the distribution of these data sets, and this was raised earlier. Our data sets are getting huge. The internet simply cannot handle moving 40 petabytes to each individual user. So our current tools and methods of storage and distribution are just not going to scale. So what do we need to go to? Something like cloud storage in containers where you write a notebook that then goes to some server and does your analysis and then gives you back the data reduction. These are the sort of things that we need to start confronting as a community. So summary and outlook, am I doing okay for time? Future of global atmospheric reanalysis. Does it have a future? I think it does, but I think most of that future is going to come, the advances are going to come by extending the length of the record and by coupling to the Earth system reanalysis. I really enjoyed Patrick's talk in particular and Danden's talk, I probably pronounced that wrong, sorry, about the Sarah system and seeing what that quasi-strongly coupled was doing to maximize the use of the observations. So I think pure atmospheric reanalysis is going to become a smaller and smaller fraction of what we see going forward, and more Earth system reanalysis. And I think that'll also help us meet these scientific needs. So some things that we need to improve. We need to improve the observations, and we need to make some decisions about which observations are going to give us the most improvement. I would suggest that if we think of a curve of gain, that when we're in the satellite era, for certain problems, say below the tropopause, we're not going to get a whole lot more out of getting more observations. For earlier, we can get a lot more. We can go a lot further, maybe 200 years. We need our models to improve so we can reanalyze and forecast better, and that representation of model error is another thing that I'm now very, very interested in because it made a huge difference, something to pay attention to. And we need better algorithms to blend the two, and as we pay more attention to the non-Gaussian aspect, say the particle filters that we saw might become more and more important. But we need ways to get to hundreds of members, maybe thousands of members to some problems, and that's where we come back to the quantum computing as well. So we need to prepare for these new computing platforms to be ready to take advantage of them. We should be using the best computers in the world and the huge data volumes. Thank you for your attention.
Thank you, Gail, for this very visionary lecture on the future of reanalysis from the atmospheric point of view. I liked your quantum computing approach. We're not quite there yet, but maybe, who knows, next conference? Okay.
Next conference.
Questions, please.
Or we can go out for a beer.
Can I start? I would like to see you doing a reanalysis of the past 30 years using just 100 observations and check how good you are to emulate the actual climate. Then I will believe that you can do a reanalysis that give us some valuable information 200 years ago. Are you planning to do it?
So currently no, because program managers don't want to fund that. That's considered boring. And it costs the same to run that as it costs to use all the surface pressure observations. That's the third most common question I get asked. So I think we have to do that, even sort of under the radar at least. But just to be fair, that Oh, this is going to help us. Never mind. Can't go back. Get a map. So here's our observation network over Europe. Here are the obs. So I think it's fair to hypothesize that, yeah, if we can hit those obs in 1815 with 10, we can probably subset to 10 in 1990. But the proof is in the tiramisu, so fair enough.
Okay, more questions for Gil.
You showed this time series on the 250 hectopascal zonal mean. And yeah, and I mean these blue lines are only surface data reanalysis, so it means that the pilot data in the 1920s didn't go into this figure.
Correct.
So
yes.
This should change.
So I would love to have a conventional, so the JRA55C and the JRA55 in this period are conventional only. To have that conventional only to put on this figure for this period through here, yeah, would be really good. Yeah, but do you hypothesize that it's going to change the conclusion?
Well, I think there are less surface pressure data as well at this time, at 1920. So, I mean, the results you showed for the 1980s maybe slightly different. I think it doesn't change the qualitatively, but maybe quantitatively you see some changes.
Any more questions for Gil? Yeah.
It's maybe more a comment than a question about your 100 data. That's exactly what we do in paleoclimate, and we make tests for the last centuries, and it works well. It's not a weather reconstruction, it's more climate for monthly mean or seasonal mean, but it works, and I'm pretty sure that we can learn from each other in this area where the coverage is nearly similar.
Yeah. Okay. Well, I guess, Gil, this was a very, very nice presentation. Thank you very much. I think you deserve another round of applause. So I guess, do we have any announcements?
Just that the program mentions 9:15, but we start at 9, okay?
So we start at 9 tomorrow morning, and Scientific Organizing Committee and LOC 8:40, not 8:30, 8:40 in the Sala Colonna for checkup. And have a nice evening. Thank you very much.